Imagine, imagine you are the lead thermal engineer on this massive next-generation aerospace project.
Right, a high-stakes scenario.
Exactly. You are tasked with designing a highly complex, internally cooled turbine blade. And this thing is operating in a combustion environment that actually exceeds the melting point of the superalloy itself.
Which is standard for modern turbines, yeah.
Right. So you spend weeks, literally weeks, building the geometry. You set it all up. You run a massive 100-hour computational fluid dynamics simulation.
Oh man, watching that progress bar crawl.
Yeah, you watch the solver iterate, and you see the energy residuals drop perfectly to zero. The software tells you, hey, the solution is converged.
Beautiful.
So you report to the project manager, you declare victory, and the team goes ahead and machines a physical prototype that costs, $1 million.
Okay, I see where this is going.
A month later, that prototype is mounted on the test stand. They fire the engine, and within 30 seconds, the turbine blade completely melts into just a pile of expensive slag.
Just completely destroyed.
Totally destroyed. And why? Because somewhere in that perfectly converged setup, you left a single invisible solver setting on single precision.
Oh, wow. Yeah.
The math basically rounded off a microscopic thermal gradient, artificially deleted a critical heat transfer coefficient right out of existence, and the software lied to you.
I mean, it is the ultimate nightmare scenario for any simulation engineer. And honestly, it happens far more often than the industry likes to admit.
Right.
We rely so heavily on the software to do the heavy lifting, that we just forget to interrogate the underlying mathematical architecture.
You just trust the default settings.
Exactly. When a solver claims it has found a solution, it simply means it has found a state where the algebraic equations balance.
Right.
It does not mean those equations actually reflect physical reality.
And that is exactly the mission of this deep dive. If you are sitting here with us today, you are a professional engineer tasked with setting up these high-level thermal simulations.
Yeah, this isn't for beginners.
No, definitely not. Our goal today is to really deconstruct the exact physics and the numerical challenges of conjugate heat transfer, or CHT.
We are bridging that gap between raw thermodynamics and the strict solver workflows inside Ansys Fluent.
Right, moving far beyond the default settings, beyond the basic tutorials. We want to establish the hard numerical guidelines you need to ensure absolute physical fidelity in your models.
We are going to tear down the invisible world of CHT.
Totally. But to do that, we have to start at the absolute foundation, right?
Yeah, before we even talk about meshing or, solver architecture, we have to understand what the solver is actually trying to calculate.
Right, the base physics.
Exactly. We're dealing with the first law of thermodynamics, the conservation of energy. But a computer cannot understand a philosophical concept like energy cannot be created or destroyed.
It needs a rigid mathematical framework.
Right. In fluid dynamics, the total stored energy in a fluid mass, which we usually denote as the variable E, is formulated as a strict sum of three separate physical mechanisms.
Right. And when we look at that total stored energy, we are really just summing up three specific things. First, the internal energy, which is the actual microscopic vibration and motion of the molecules themselves.
It's the literal heat, essentially.
Exactly. Then you have the kinetic energy, which is the macroscopic movement of the fluid mass, calculated as velocity squared over 2. And finally, the potential energy, which is driven by gravity.
Yeah, and it sounds so simple when you describe it physically.
It really does.
But the complexity just explodes when you ask the software to map the actual mechanisms of heat exchange, so conduction, convection, and radiation, onto that mathematical framework.
Yeah, let's take conduction, for example.
Right.
Whether the heat is moving through the solid turbine blade or diffusing through the boundary layer of the fluid, the solver relies fundamentally on Fourier's law.
Yes.
Fourier's law basically dictates that the heat flux, the actual amount of energy moving through a given area, is directly proportional to the temperature gradient.
Exactly. If one side of a cell is hot and the other is cold, the heat wants to move.
Right. And the proportionality coefficient that governs how easily that heat moves is the thermal conductivity, denoted as K.
Yeah, that K value is critical. And then you have convection, which is where the fluid physically carries the heat away.
Right, mass transport.
The mathematical description of this manifests through the convective terms in the differential equations, which are entirely driven by the velocity field. The fluid moves, and it just takes the internal energy with it.
But here is a real-world dilemma I see engineers stumble over constantly with this.
Oh, yeah?
We treat convection and conduction as these separate, clean mechanisms in our heads.
Right.
But what happens when that velocity field is extreme? Say you are looking at a scramjet inlet in a high-Mach aerospace application.
Okay, supersonic stuff.
Yeah, or maybe a high-speed journal bearing that's just heavily loaded with viscous lubricating oil. But the standard convective terms in the energy equation simply are not enough to capture the reality of the temperature field there.
No, they absolutely aren't. Because in those extreme regimes, you are generating heat out of thin air through viscous dissipation.
Right, viscous dissipation.
We denote this mathematically as food. Imagine the fluid as thousands of microscopic layers stacked on top of each other.
Like a deck of cards.
Exactly, like a deck of cards. In a high Mach flow, or a highly viscous flow, those layers were sliding past one another at just drastically different speeds.
Right.
The sheer friction of those layers rubbing together actually does work. And thermodynamically, the work of those viscous forces is non-reversible. It converts directly from kinetic energy into internal energy.
It literally becomes heat.
Yes, it becomes heat.
And this is exactly where the software defaults will completely betray you.
Oh, absolutely.
In the Ansys Fluent setup under the viscous model window, there is a specific option called viscous work.
Yes, that little checkbox.
Right. The
Yeah.
solver will not turn this on for you automatically just because you enabled the energy equation.
No, it won't.
If you are modeling a high-speed aerodynamic flow or a really tight lubrication clearance, and you fail to explicitly check that viscous work box, the solver will completely ignore the friction between the fluid layers.
It just pretends it doesn't exist.
Exactly. And your resulting temperature field will be artificially low, and your structural team will end up designing a component that fails under the real-world thermal load.
It's a massive trap. And that leads directly to how we define the materials themselves, too.
Right, the material definition.
The thermal conductivity, that K value we mentioned earlier, and the specific heat capacity, CP.
Right.
Those dictate the thermal inertia of your system. They dictate how much energy a material can absorb and how fast it can transfer it.
Yeah.
A massive trap engineers fall into here is treating these properties as constants.
Oh man, you see it all the time. Someone looks up the thermal conductivity of like standard steel at room temperature.
Right, 20 degrees Celsius.
They type that constant into Fluent, and then they run a simulation where the component hits 800 degrees Celsius.
Which is just mathematically fatal to your accuracy.
Completely fatal.
As the temperature of a solid changes by hundreds of degrees, the microscopic lattice vibrations, the phonons that actually carry the heat, they behave differently.
Right, the physics change.
Exactly. The material's ability to store and diffuse energy changes fundamentally. Defining specific heat and conductivity as constants when you are dealing with large temperature gradients, it means you are solving a perfectly accurate set of thermodynamic equations for a fictional material.
A material that does not actually exist in your real-world operating envelope.
Precisely.
Yeah.
You absolutely must use temperature-dependent functions, either polynomial curves or piecewise linear points, to define these properties in the software.
Right, you have to feed it the curve. And that material definition gets even more complicated when we step away from simple isotropic metals and look at advanced materials.
Oh, definitely.
Think about the stator inside an electric motor.
Okay.
It is packed with tightly wound copper wire, and that wire is impregnated with insulating epoxy.
A very complex composite.
Right. Heat does not travel uniformly through that mass. It travels incredibly fast along the continuous length of the copper wire, but it really struggles to travel outward across the layers of epoxy and all those tiny air gaps.
So it's highly direction dependent.
Exactly. The heat flux is highly direction dependent. It is anisotropic.
Right.
If you try to model every single microscopic wire and gap, your mesh will require billions of cells. It's impossible.
No computer can handle that.
Right. So we homogenize the geometry into a single solid block. But then the question is, how do we tell the solver that the block transfers heat differently in the x direction than the y direction?
Well, this is where we define a curvilinear coordinate system, or CCS.
Okay, a CCS.
By mapping a CCS to the solid's material orientation in Fluent, you are radically altering Fourier's law under the hood.
How so?
You are telling the solver that the thermal conductivity K is no longer a simple scalar number. You are actually replacing it with a spatial tensor matrix.
Oh, wow. Okay.
Yeah, so the software now evaluates the direction of the temperature gradient in every single cell, checks that tensor matrix to see the conductivity in that specific direction, and calculates the heat flux accordingly.
That's incredibly powerful.
It is. It's a brilliant mathematical abstraction that allows you to model complex composite behavior without needing a supercomputer to mesh the actual microscopic geometry.
Okay, so we have established how heat wants to move through the materials, right? And we have thermodynamics defined.
Right.
But material properties only dictate the potential for heat transfer. When that solid physically touches the fluid, the mathematical continuum hits a literal wall.
Yes, the interface.
And this brings us to what I consider the most critical physical domain in any CHT simulation, the thermal boundary layer.
Oh, absolutely. This is where the mesh dictates the physics.
Exactly.
The boundary layer is really the battleground of conjugate heat transfer. As fluid flows over a solid surface, you have the no-slip condition.
Right, the no-slip condition.
This dictates that the fluid molecules directly touching the wall has zero velocity relative to the wall.
Right, they are stuck to it.
Yes. So the velocity drops from the free stream speed all the way down to zero across a microscopic distance. In this extremely thin region, viscous effects completely dominate.
Yeah.
The way energy moves fundamentally changes there, from mass convection to pure microscopic conduction.
Right.
If your computational grid, your mesh, cannot mathematically resolve that shear gradient, your shear stress and your heat transfer coefficients are fundamentally broken.
Totally broken. So how do we actually translate that physical boundary into a mathematical grid?
Well, we rely on the dimensionless wall distance.
Right, what we call y plus or y.
Exactly.
It is a parameter that ties the physical height of your first mesh cell directly to the local velocity, viscosity, and shear stress of the flow. Now, I want to talk about how to actually build that mesh.
Yeah, let's get into the workflow.
When setting up the geometry, engineers always face the debate of conformal versus non-conformal interfaces between the fluid region and the solid region.
It's a constant argument.
I heavily insist on a conformal interface for CHT.
I agree completely.
You achieve this using the share topology feature in Ansys Space Claim or Fluent meshing. This ensures direct node-to-node continuity.
Right.
The corner of a fluid cell physically shares the exact same coordinate space as the corner of the solid cell.
And for high-fidelity CHT, that node-to-node continuity is virtually non-negotiable.
Why is that mathematically?
Because if you use a non-conformal interface, where the mesh of the solid and the mesh of the fluid do not perfectly align, the solver is forced to interpolate the energy values across those misaligned cell faces.
Right, it has to guess the values between the nodes.
Exactly, and interpolation inherently introduces numerical diffusion.
Yeah.
It smears the gradient.
It blurs the physics.
Physically, this acts like an artificial layer of thermal resistance between your fluid and your solid. Yet you will get a temperature jump at the interface that is purely a numerical artifact, not a physical reality.
That is unacceptable if you want accurate heat transfer. So to capture that heat flux accurately without that numerical smearing, we really have to establish hard numerical guidelines for your inflation layer.
Yes, the inflation layers are key.
The specialized structural cells, usually prisms or hex cores that hug the wall.
Right.
If you are listening to this, you might be thinking, I don't have the computing power to put a massive, dense inflation layer on a complex industrial geometry.
It's a valid concern. Meshes get huge quickly.
It is a fair point. But here's the risk you take if you compromise. If you are using advanced turbulence models like SST Omega or Speller Almaraz, the absolute minimum requirement is 10 structural layers strictly inside the physical boundary layer.
10 layers, minimum. And let us put strict mathematical boundaries on that too.
Okay, yeah.
If you are going for high thermal fidelity, meaning the heat transfer coefficient is the primary goal of your simulation, and you are using enhanced wall treatment, or EWT.
Right.
Your Y plus value must be approximately 1.
Approximately 1.
That is not a suggestion. It is a hard rule to resolve the viscous sublayer.
Right.
Now, if extreme computational limits absolutely force you to use standard wall functions, your Y plus must sit strictly in the log-law region where turbulence dominates the momentum transport.
And what are the numerical bounds for that?
That means your first cell's Y plus must be strictly between 30 and 300.
Okay, so this is something I always struggle with, the transition zone between those two guidelines.
Buffer zone.
Yeah. Everyone in the industry regurgitates the rule. Keep your Y plus around 1 or put it above 30. But mathematically, what is actually happening in the middle there? Why is a Y plus of, say, 15 so toxic to the solver?
It comes down to the physics of the buffer zone. Between a Y plus of 1 and 30, the fluid is in a state of chaos.
Okay.
It is transitioning from viscous-dominated laminar flow near the wall to turbulence-dominated flow further out.
Yeah.
Neither molecular viscosity nor turbulent eddy viscosity actually dominates in that specific zone. The empirical wall functions programmed into the solver are mathematically derived, assuming one regime or the other.
Is that?
So if you place the center of your first mesh cell directly in that buffer zone, say at a y plus of 15, you are feeding the mathematical equations a physical state they just cannot resolve.
They aren't built for it.
Exactly. The empirical formulas become fundamentally unstable, and they will mathematically corrupt your heat transfer calculations.
So you just get garbage data for your heat flux.
Pretty much.
And, it isn't just about where you place that first cell, right? It is also about how the cells grow outward from the wall into the free stream.
Yes, the growth rate.
When you set the offset method type in your meshing tool, your volume growth rate must never exceed 1.2.
Never.
And if you are using transition SST models to capture delicate laminar to turbulent transitions, that growth rate needs to be tightly capped at 1.15.
We need to explain why that 1.2 growth rate matters physically, though.
Yeah, please do.
The solver calculates the flow of heat by comparing the energy value at the center of one cell to the energy value at the center of the adjacent cell.
Right.
This is how it calculates the spatial gradient. If cell B suddenly has double the volume of cell A, the physical distance between those cell centers jumps drastically.
So the distance parameter in the derivative is suddenly huge.
Exactly. The mathematical gradient is stretched over an artificially long distance. The derivatives in your energy equation become highly inaccurate through Taylor series truncation errors.
Truncation errors, right?
The solver essentially thinks the heat is struggling to travel further than it actually is, which creates a false thermal blockage.
A false thermal blockage. That is a great way to put it. Okay, so assuming we have respected the thermodynamics, we have a perfect conformal mesh with node-to-node continuity. Our y plus is exactly 1, and our growth rate is a smooth 1.15.
A perfect setup so far.
Right. How does the solver actually handle the transfer of energy when the fluid domain physically touches the solid domain?
The interface mechanics.
Yeah. In Fluent, when a fluid region and a solid region share that conformal topology, the software automatically creates what is called a wall and wall shadow pair.
Yes. To understand the shadow pair, you really have to think about how the computer physically stores the geometry in its memory.
Right.
The fluid domain requires an energy equation to be solved, and the solid domain requires a completely separate energy equation to be solved. They are two different zones.
But they share one physical boundary in the real world.
Exactly. By creating a wall assigned to the fluid and a wall shadow assigned to the solid, the solver basically creates two overlapping mathematical faces occupying the exact same space.
It's like a duplicate face.
Right. It gives the software a way to pass information back and forth between the two different equations.
Okay, but for CHT to actually function across that shadow pair, the thermal boundary condition for these interface zones must be explicitly set to coupled.
Yes.
Why coupled specifically? What is the software doing differently than if I just set, say, a fixed temperature?
When you select coupled, you are removing all external user constraints.
Okay.
You are forbidding the solver from using a fixed temperature or a fixed heat flux that you defined. Instead, you are instructing the solver to directly compute the heat transfer across the phase boundary iteratively.
So it's dynamically calculating it.
Yes. At every single computational step, the solver calculates the Fourier conduction reaching the interface from the solid side, and it calculates the convective heat flux reaching the interface from the fluid side.
Right.
It compares the two. If they do not match, it adjusts the local temperature field and tries again. It iterates continually until the heat leaving the solid exactly equals the heat entering the fluid.
It forces the energy balance to close at the interface.
Precisely.
But there are scenarios where explicitly meshing a solid zone to calculate that Fourier conduction is just computationally absurd.
Oh, definitely.
Let's talk about thin physical layers. Imagine a thick steel pipe carrying hot fluid, but the pipe is coated in a 1 millimeter layer of anti-corrosive thermal paint.
Okay.
Or perhaps a thin thermal barrier coating on our turbine blade from the earlier example. If you try to build a 3D mesh inside a 1 millimeter coating across a massive industrial domain, you will literally drive your cell count into the hundreds of millions for almost no physical benefit.
It's completely inefficient, and this is exactly where the thin wall boundary condition is mathematically brilliant.
How does it work?
Instead of building a physical 3D mesh for that coating, you simply select the fluid-solid boundary, you define a wall thickness of, say, 1 millimeter, and you assign the material property of the paint.
So no cells are generated for the paint.
Right. The solver does not generate a single cell. Instead, it computes a one-dimensional Fourier's law thermal resistance strictly in the normal direction.
Through the thickness.
Exactly. It analytically calculates the temperature drop across that virtual thickness before passing the remaining heat flux into the fluid.
Wow.
It provides the exact thermal resistance of the coating while saving you immense computational overhead.
It essentially treats the coating as a pure mathematical resistor.
That's a perfect analogy.
And if we extrapolate that analogy, what if the heat doesn't just travel straight through the wall in the normal direction, but it also travels along the plane of the wall?
Okay, tangential conduction.
Yeah.
Yeah.
Imagine a thin sheet metal casing surrounding an electronics box. The casing conducts heat tangentially from a hot spot to a cooler area. For that, we use shell conduction.
Right, shell conduction.
You can define multiple virtual conduction layers in the boundary condition, and the solver will dynamically compute the heat transfer in the tangential planar directions.
So it's spreading the heat out.
Exactly. It basically solves a 2D conduction equation over the surface of your 3D mesh, allowing the casing to spread heat laterally, all without adding a single structural cell to your actual volume mesh.
It is an incredibly elegant mathematical abstraction.
It really is.
But, as we define these boundaries and interfaces, we also have to account for energy sources and sinks within the volumes themselves.
Right.
Volumetric heat sources, like Joule heating in an electrical busbar or chemical exothermic reactions, these are defined in the cell zone conditions.
Yes, and I really want to highlight a massive trap here for engineers setting this up in Fluent.
The unit conversion trap.
Exactly. Fluent requires the volumetric heat source to be defined in watts per cubic meter.
Right.
If you have a data sheet that says a microchip generates 50 watts of heat, you cannot just type 50 into the energy source box.
Please don't do that.
Right, because if you do, you are telling the solver the chip generates 50 watts per cubic meter, which will result in almost zero actual heat generation in a tiny chip.
Because the chip's volume is a fraction of a cubic meter.
Exactly. You must manually divide that total wattage by the exact computational volume of the zone, which you can pull directly from the volume integrals report, and then you input that calculated density.
It is such a common mistake, and it just totally invalidates the thermal profile.
Totally invalidates it.
But speaking of mistakes at the boundaries, let us move to the edges of the simulation domain.
Okay, let's talk about the outlets.
Yeah. There is a specific physical phenomenon at the outlet that causes countless CHT simulations to inexplicably diverge, and that is the backflow temperature setting.
Oh, the backflow. Right. During the iterative solving process, the pressure field is constantly updating, constantly shifting.
Yes.
Before the flow stabilizes, it is incredibly common for adverse pressure gradients to form at the outlet, which basically causes fluid to momentarily re-enter the domain from the outside.
And this backflow is a critical physical necessity of the iterative process.
Right.
But if you have not defined a realistic backflow temperature in your boundary conditions, the solver just assumes the fluid entering from the outside is at the default temperature.
Which is usually 300 Kelvin ambient.
Exactly. So imagine your internal flow is a hot exhaust gas at a 1000 Kelvin.
Okay.
The moment that iteration triggers backflow, 300 Kelvin fluid mathematically slams into your 1000 Kelvin domain. It creates an instantaneous non-physical thermal shock. The massive temperature gradient spike the energy equations, the density fluctuates wildly, and your residuals will just oscillate violently until the solver crashes.
So what's the fix?
You must set a backflow temperature that closely approximates the expected outlet temperature to prevent this mathematical shockwave.
Okay, let's take a breath and unpack where we are.
We've covered a lot of ground.
We really have. We have mapped our thermodynamics. We have generated a mathematically sound conformal mesh. We have coupled our interfaces and established our volumetric sources and thermal boundary conditions.
The physical architecture is complete.
Right. Now, the algebraic equations actually have to be solved.
The solver itself.
Yeah. This brings us to the solver architecture. In the general setup window, the first major decision is choosing between the pressure-based solver and the density-based solver.
A fundamental choice.
Pressure-based is your historical workhorse for incompressible flows or mildly compressible flows. Density-based is a highly specialized architecture explicitly designed for supersonic flows where shock waves create extreme discontinuous density gradients.
Right, and the underlying physics of the fluid dictate this choice.
Exactly.
In a density-based solver, The continuity equation, the momentum equations, and the energy equation are strongly coupled together into a single vector system.
They all solve at once.
Yes, they are solved simultaneously because in a supersonic shock wave, a change in pressure causes a massive instantaneous change in temperature and density.
Right.
But for the vast majority of CHT applications, even high-temperature gas flows, we use the pressure-based solver.
Because there are no shock waves.
Exactly. In this architecture, the energy equation is often solved sequentially as an additional scalar after the pressure and momentum fields are updated.
However, just because it is solved as a scalar does not mean it is independent.
Oh, no, not at all.
The mathematical coupling of the energy equation back to the momentum field is profound in CHT.
Very profound.
A change in the temperature field alters the local fluid density and the dynamic viscosity. Those updated fluid properties fundamentally alter the velocity field, which in turn changes how the fluid convects heat, which then updates the temperature field again.
It is a relentless feedback loop.
Because of that tight, non-linear loop, using a segregated scheme where the solver updates pressure, then velocity, then energy, one by one,
Right.
that can take tens of thousands of iterations to converge, or it might just oscillate indefinitely.
It just chases its own tail.
Exactly. That is why, for CHT stability, the coupled pressure-velocity scheme is highly superior.
Agreed.
By solving the pressure and momentum equations simultaneously as a single matrix, it drastically accelerates the stabilization of the velocity field, which in turn anchors the energy field.
But there is one solver setting in the general architecture that is absolutely not up for debate.
The big one.
It is the most critical setting we will discuss today.
Double precision.
It truly cannot be overstated. Double precision, which is instructing the software to use a 64-bit representation for floating point numbers instead of a standard 32-bit float, is not an optional feature for thermal simulations.
Right.
It is a strict mathematical mandate.
Using single precision to calculate CHT is like trying to measure the exact distance to the moon, but your ruler only has mile markers, and you need to measure down to the millimeter.
That's a great analogy.
You just do not have the decimal places to capture the massive scale and the tiny detail at the exact same time. But what is actually happening in the computer's memory that causes single precision to fail so spectacularly?
Well, it comes down to how a computer stores a number.
Okay.
It divides it into an exponent and a mantissa,
Okay.
and that impacts how it handles closing the energy balances.
Right.
In CHT, you frequently deal with extreme contrasts in magnitude.
Give me an example.
Imagine you are simulating a microscopic water cooling channel inside a massive solid block of high-grade copper.
Okay. Extreme contrast there.
Right. The thermal conductivity of copper is thousands of times higher than water. The rate of heat transfer through the solid is immense, while the boundary layer differentials in the water are tiny.
Okay, I see.
Or consider a completely different scenario,
Yeah.
antral convection inside an electronics enclosure.
Right, cooling a server box.
Exactly. The pressure gradients driving the buoyant flow of the hot air are infinitesimally small. A 32-bit single precision solver simply does not have the available decimal places to resolve massive heat fluxes and tiny pressure differentials simultaneously.
So what happened?
When the solver tries to add a very small number to a very large number, the small number is literally truncated.
Just delete it.
It is chopped off. Those truncation errors accumulate with every iteration, and suddenly heat just disappears from your simulation. You physically violate the first law of thermodynamics within your own computer's memory architecture.
Wow. Okay, so double precision is checked. 64-bit math is on. The energy is mathematically conserved.
Step 1 complete.
Right. Next, we have to manage the numerical stability of the iterations themselves through under-relaxation factors, or URFs.
Oh, the URF.
Yeah. URFs are essentially a mathematical brake pedal. They control how much a variable is allowed to change from one iteration to the next.
Right.
Now, a lot of engineers, when they see their residuals spiking or oscillating, they immediately open the URF panel and drop the factors to force the math to calm down.
Which is an incredibly dangerous habit.
Why is it dangerous?
Let's look specifically at the energy URF. The default value is 1.0, meaning the solver applies 100% of the newly calculated temperature field to the next iteration.
Right.
For CHT simulations with extreme material contrasts, like our water and steel example,
Oh,
or in
yeah.
cases heavily driven by delicate natural convection, the solver might overpredict the temperature change in a single iteration, which causes instability.
So you might need to lower it?
You might.
Yeah.
But the energy URF must sit tightly between 0.95 and 1.0.
What actually happens if someone gets frustrated with oscillating residuals and drops the energy URF down to, say, 0.7 to 0.5?
You artificially freeze the temperature field.
Freeze it.
Yeah. By dropping the URF to zero 0.5, you are telling the solver it is only mathematically allowed to apply 50% of the calculated heat transfer per iteration. You are strangling the energy equation.
Wow.
Because the temperature is barely allowed to change between iterations, the solver calculates that the error, the residual, is incredibly small.
Ah, so it looks good on the graph.
Exactly. Your residuals will violently plummet to 1e6. It gives you a false illusion of perfect rapid convergence.
It's a lie.
A total lie. The physical temperature field has not actually evolved to its steady state. You end up with a fundamentally inaccurate heat transfer rate because you forced the solver to stop calculating before the heat actually reached its destination.
That is terrifying. Okay, so keep the energy URF near 1.0. Also, to avoid numerical diffusion during these spatial calculations, our spatial discretization for energy and momentum should be set to second-order upwind.
Yes, second-order upwind is standard for CHT.
This uses a multidimensional linear reconstruction approach to calculate the gradients, rather than just looking at the immediate upstream cell.
Right.
And if we are dealing with that buoyancy-driven natural convection we mentioned, specifically under the Boussinesq approximation, we need to alter our pressure interpolation.
Yes, let us explain the Boussinesq approximation conceptually first.
Go for it.
In natural convection, fluid heats up, its density decreases, and it rises.
Basic buoyancy.
Right. But calculating a new density for every single fluid cell based on temperature takes massive computing power. The Boussinesq model is essentially a computational cheat code.
The cheat code?
Yeah, it treats the entire fluid density as a constant, dramatically speeding up the continuity equations. It only applies the density changes as a virtual gravity body force in the momentum equation.
Oh, that's clever.
It is, but you can only use this cheat code if the density variations are small, meaning the volumetric expansion coefficient multiplied by the temperature difference is much less than 1.
Okay, and when you use that Boussinesq body force, the standard pressure interpolation scheme fails.
It does.
You must change the pressure interpolation scheme in the solver to Presto, or body force weighted.
Presto is usually my go-to.
Right. Presto ensures the solver physically calculates the pressure exactly at the cell faces, which is critical to capturing the delicate momentum shifts caused by those localized gravity-driven body forces.
And, before you even hit the calculate button, establishing a realistic preliminary temperature field can save you thousands of iterations of compute time.
Initialization.
Exactly. In complex assemblies like multipass cross-flow heat exchangers, initializing the entire domain with a flat 300 Kelvin guess forces the solver to slowly push heat through the entire system from scratch.
It takes forever.
I always recommend using full multi-grid, or FMG, initialization.
You have to trigger it through the text user interface in Fluent.
Yes, the TUI. It solves simplified and viscid continuity and energy equations on a mathematically coarsened mesh hierarchy to give the solver a highly realistic starting guess.
So it preheats the domain, mathematically speaking.
Basically, it effectively primes the thermodynamic pump before the complex iterations begin.
That's a great tip. But up until now, we have really only been talking about linear or near-linear thermal mechanisms.
Conduction and convection.
Right. This raises a critical question for high-temperature engineering. What happens when we introduce radiation into this perfectly balanced continuum?
This is where the physics become intensely volatile.
Volatile is a good word.
Radiation is fundamentally different from conduction or convection. Those mechanisms scale linearly with the temperature difference between 2 points.
Right, delta T.
But radiation, governed by the Stefan Boltzmann law, scales with the fourth power of the absolute temperature, T to the fourth.
T to the fourth, that's a massive curve.
It is. If you double the absolute temperature, the radiated heat flux does not double. It increases by a factor of 16.
Wow.
It introduces a massive compounding nonlinearity to the energy equations.
To even begin to model it, we have to define the physical properties of the materials emitting the photons, right?
Yes.
First is emissivity, denoted by epsilon. In Fluent, we generally use the gray diffuse surface model.
Correct.
This assumes that the energy emitted by a surface is a specific fraction of a perfect idealized black body.
Right.
Crucially, the gray diffuse assumption means that the emissivity is equal to the absorptivity and that the radiation is emitted equally in all directions, independent of the physical wavelength.
That defines the solid surfaces. But then we have to consider the volume itself, the actual fluid space sitting between the solids.
Right, the air or the gas.
Is the fluid transparent to the photons? Or is the fluid a dense exhaust gas filled with soot that absorbs the heat?
And this physical reality is dictated by a parameter called optical thickness.
Exactly. Optical thickness is the single parameter that determines your entire radiation solver strategy.
Oh, so
Conceptually, it is the product of the physical distance the light has to travel, the optical path length, and the sum of the absorption and scattering coefficients of the fluid.
okay, give me an example.
If your domain is a server room filled with clean, dry air, the absorption coefficient of that air is virtually zero. The optical thickness is mathematically zero.
We call that an optically thin medium.
Right. It is like looking through clear glass.
For an optically thin medium, we use the surface-to-surface, or S2S, radiation model.
S2S, yes.
Because the fluid does not absorb the photons, S2S ignores the fluid volume entirely. It relies strictly on geometric view factors.
Right.
It analytically calculates how much of surface A physically sees surface B, and calculates the energy exchange between those two boundaries. But what if the fluid is not clear air? What if it is a dense, opaque combustion gas inside an industrial furnace?
Then the medium is actively absorbing and emitting radiation itself. It is like trying to shine a flashlight through heavy fog.
Right, optically thick.
The medium is optically thick. In this case, S2S is physically invalid.
Because it ignores the fluid.
Exactly. You must use the discrete ordinates, or DO, model. The DO solver is incredibly versatile because it physically solves the radiative transfer equation for a discrete number of angular directions through the fluid volume.
So it tracks the rays through the fog?
Yes, it accounts for the gas absorbing the heat and re-radiating it. It works across the entire physical spectrum of optical thicknesses.
What about the P1 model?
Alternatively, if the fluid is extremely optically thick everywhere, a truly dense, opaque medium, you can use the P1 model, which is a mathematically simplified, faster approximation that treats radiation almost like an additional diffusion equation.
Okay, so when you configure radiation in the Fluent interface, there are strict best practices that engineers often overlook until their simulation crashes.
So many crashes.
First, radiation equations demand absolute temperature scales. Kelvin or Rankine.
Yes.
If you are operating your Fluent interface in Celsius, you must open the general operating conditions and explicitly verify that the temperature offset is exactly 273.15.
Do not forget this step.
Right. If this is even slightly wrong, your T to the fourth calculations will be catastrophically magnified, and the solver will instantaneously diverge.
It will blow up immediately.
And if you are using that discrete ordinates model, we need to address angular discretization.
Right, the ray traces.
The DO model breaks the 3D spherical space into discrete angular ray divisions, theta and phi. The default setting in Fluent is a 2x2 discretization.
Which is almost always far too coarse for a high-fidelity CHT simulation.
Exactly. Why does 2x2 fail?
Think about the physics of a shadow. A 2x2 division means the solver is only shooting a very limited number of rays across the domain to calculate the photon transfer.
Right, just a few discrete beams.
If you have complex geometries, cooling fins, intricate pipe routing, or tight clearances, those sparse rays will literally miss critical surfaces.
They just bypass them.
Yeah, you will get harsh, jagged gradients where one cell receives a massive heat flux and the adjacent cell is completely shadowed purely because a ray missed it.
Oh, that makes total sense. So what's the fix?
You must increase those angular divisions to at least 3x3 or 5x5 to ensure enough directional resolution to physically capture the radiative flux.
And because of that T to the fourth nonlinearity, your convergence criteria for the energy equation must be heavily tightened.
Absolutely.
The standard default of 106 is no longer mathematically sufficient to guarantee energy conservation. You must explicitly mandate a residual of 108 to properly manage the radiative energy balance.
Otherwise, small mathematical errors in the temperature field will mathematically snowball into massive heat flux errors.
Exactly. Which brings us to the ultimate reckoning for any CFD engineer.
The moment of truth.
After you have implemented double precision, fix your Y plus at 1, meshed your conformal interfaces, and run the DO radiation model, how do you definitively prove your CHT simulation is physically accurate?
Right. How do you prove it is not just mathematically converged, but actually thermodynamically valid?
Because there is a massive danger in the industry of relying solely on residual drops. People watch the graph go down, hit the default limits, and immediately declare victory.
Just like our turbine blade example.
Exactly. But what is a residual fundamentally?
A residual is simply a mathematical measure of the non-physical imbalance in the algebraic equation for a specific mesh cell.
It is the error left over after a single iteration.
Right. As we mentioned, for CHT, energy residuals must reach 106 and preferably 108. But low residuals only mean the solver has found a mathematical equilibrium for the equations it was given.
It means the math has stopped changing.
Exactly. It does not mean those equations reflect reality.
So what is the ultimate truth?
The thermodynamic ledger.
The flex balance test.
Yes.
After the simulation converges, you must generate a fluxes report from the results tab.
Yeah.
You select total heat transfer rate and you highlight every single thermal boundary in your entire domain. Inlets, outlets, walls, radiation surfaces.
And here is the hard, unbreakable rule of CHT validation. The net imbalance of the total heat transfer rate across the entire domain must be strictly less than 1% of the smallest boundary flux.
Less than 1%.
The physical energy going into the domain minus the energy going out plus any volumetric heat sources must sum to 0.
Right, conservation of energy.
If your net imbalance is greater than 1%, you have a computationally leaky domain. Energy is mathematically vanishing or appearing out of nowhere.
And if that error is greater than 10%?
The physics are fundamentally divergent.
It does not matter if your residuals are sitting flawlessly at 1E10. Your simulation is physically invalid.
Right. A massive flux imbalance usually points directly back to a poorly constructed boundary layer mesh, destroying the gradient calculation, or incorrect under-relaxation factors artificially freezing the field.
Or the fatal flaw of failing to use double precision.
Or it points to severe numerical instability triggering the solver's hard-coded limits.
Ah, yes.
Every CFD engineer has eventually checked the Fluent text console and seen the dreaded warning.
Temperature limited to 1.000000000 plus 00 in X cells.
The pegging warning. It is terrifying.
It really is. The solver is hitting the default thermodynamic limits, which are hard-coded at 1 Kelvin for the minimum and 5,000 Kelvin for the maximum.
Right.
When the solver warns you that it is limiting the temperature, it means the mathematical matrix in those specific cells resulted in a temperature below absolute zero or hotter than the surface of a star.
That pegging is the solver essentially mathematically panicking.
Yeah.
It is a symptom of severe instability, usually caused by a divide by zero error or a massive gradient distortion in a highly skewed cell.
So what do you do?
When this happens, you cannot just ignore it. You require immediate cell register analysis.
Right.
You have to isolate those specific cells and interrogate the mesh quality. Specifically, the cell skewness must be less than 0.9 and the orthogonal quality must be greater than 0.1.
And once you fix the mesh,
you must verify grid independence to prove that further refining the cell count does not drastically alter your maximum temperature predictions.
So what does this all mean for you, the engineer? We started by talking about how conjugate heat transfer lacks the visual mechanical intuition of pure fluid dynamics.
Right. You can't just look at a flow field and guess the temperature perfectly.
Exactly. You cannot visually see the temperature fields forming until you explicitly extract them mathematically. To do that accurately, you have to build the entire numerical architecture perfectly.
From defining temperature-dependent physical properties to building a strict 10-layer conformal boundary mesh with a y plus of 1.
To locking in a 64-bit double precision pressure-coupled solver, every physical phenomenon must have a corresponding mathematically rigorous boundary condition.
And this leads us to a much larger philosophical challenge about how we model reality.
Let's hear it.
We have spent this entire session defining the absolute necessity of meshing the precise physical geometry.
Right, resolving the boundary layer perfectly.
But if defining explicit solid zones with conformal meshing and exact I+ values is so computationally demanding, consider the physics of porous media non-equilibrium models.
Oh, this is a fascinating extrapolation.
It really is.
In the porous media approach, Fluent allows you to skip explicitly meshing the solid geometry entirely.
Right.
Instead of building a complex mesh for a massive car radiator or a tightly packed catalyst bed, you treat the entire volume as a fluid zone with a porous resistance.
But thermodynamically, you solve two entirely separate energy equations within the exact same computational space.
Exactly. One equation for the fluid moving through the volume, and one equation for a virtual, completely unmeshed solid matrix.
The two separate equations are coupled purely by a mathematical source term based on interfacial area density.
Wow.
It forces you, as the engineer, to ask a critical boundary question. When is resolving the exact microscopic boundary layer absolutely necessary to the survival of your component? And when can the physical microstructure of the solid simply become a homogenized mathematical abstraction in the momentum and energy equations?
It is the ultimate trade-off between physical exactness and computational pragmatism.
It really is.
And it reminds us that in computational fluid dynamics, the X-ray machine is only ever as good as the physics you program into it.
Absolutely.
Do not let the software make assumptions for you. Respect the thermodynamics, enforce double precision, and always, always trust the physical flux balance over the mathematical residuals. Until next time.